I can show you a little bit of what you can, yeah, kind of how you can, issues you may encounter and possible solutions to when you want to scale your PyTorch training to, really large scales, meaning like thousands or tens of thousands of GPUs or more. So that put a lot of stress on the HPC system, and especially on two key aspects. One is communication, because in order to keep your model in sync as you process your data, each GPU must communicate their updates to the others, and those have to be aggregated. And so when you have tens of thousands of these messages being sent, this can put the network to stress. And then depending on your application, there can be problems with input output. So when all of your GPUs need to, or all of your processes, let's say, have to read something from the file system, especially if they want to read on the same file on a shared file system, that can cause like issues, hangs, and things like that. So there could be other problems, of course, but these are two of the most common, and I'm gonna cover a little bit how you can solve or at least things you can try to mitigate those issues. The first one is communication, and as I said, we use so PyTorch uses 1CCL so which is the one API collective communication library for collective operations like all reuse. And so this library comes with several different algorithms for each of these operations. So there are several ways you can do all reduce, and each of these algorithms can also have different variables you can set, for example, about the sizes of the messages and so on and so forth. Our team has done several tests to measure the performance of these different 1CCL algorithms and configurations when training a variety of deep learning models at scale, meaning on several thousands of nodes. What they've seen is that the best configuration usually is application dependent, but they have identified a set of optimal settings that usually works well for most of these applications. And you can find the complete list on, again, the docs on the 1CCL section. But we also make them available via this frameworks optimize module. So this module is basically the frameworks module with a bunch of environment variables that are set based on this testing for the optimal settings. It works under a series of assumptions, for example, that you're running with 12 ranks per node. And of course, if you want to change any of these environment variables, you're welcome to override the corresponding environment variables. So for example, the library also set the CPU bindings. If you want to try different bindings, you can override the default one. I don't think I will show. So basically, you can repeat what we've just done here using this framework optimized. You shouldn't see any difference when we're on two nodes, actually, but you may see quite an improvement with respect to the base settings when you run on thousands of nodes. The second thing to discuss is input-output, which means reading a file, but also more trivially importing a Python module from disk. So when you run import torch, for example, then there is a process that goes and fetch from the disk the torch library, the torch code, and so on. And so if all of the ranks are trying to get to access the same file, this can stall your application at the import stage, especially if you use the Lustre file system. This is not an issue when you use the frameworks module, because that is not on the Lustre file system. It's on each compute node image. So you don't encounter this issue with the frameworks module. But if you create a custom environment for your application, you may see a lot of slowdown when you which may look similar to what you see in this table. So when you run on 64 nodes, and this is, I guess, an environment with just a custom installation of the torch. This is not the frameworks module, but a user created environment with torch. This can be any other Python library. But if it's big enough, as you increase the number of nodes you run your application on, you can see that also the time to that it takes to import the library increases pretty steadily. On the last column, you see that instead the loading time is pretty stable if you use this tool that is called Copper, that allows to basically read, so load the library. So it's only one of your nodes will actually go to the Lustre file system to load the library. And then this node will distribute the loaded file to all of the other nodes. So the impact on the file system in this case is just minimal, because it's only one node access the file. Again, this is only Copper is only needed if you are you loading your own libraries, and not if you use the frameworks module. And the benefit of Copper can vary depending on the the module, the application, but definitely clear for more than for thousands of nodes. But again, it's something you can try even if you run on slower node number of nodes, lower number of nodes. So in the examples folder, you have an example of using Copper to load this user-defined torch environment. So in the example, let me open it up. So we only used 2 nodes because just to give others the opportunity to try, but you can change this if you want to pass on more nodes. And what this is doing is launching Copper, which you can you have to first load the Copper module and then run the launch copper.sh script, which is activated as you load the Copper environment. Assuming that you have your local Conda environment in some location, you put this location, we call this location last Conda path. And then if you want to use Copper to import this library, then you have to append, so prepend to your Python path, actually, the Conda path, where you have prepended to it this temp user, your name, your username, and then the /copper. So this will create, will mount an image to this location, and will and this is where your Python will look for the library instead of on the Lustre file system. And then, so you have to pass this thing, you can pass it on the MPI exec command like this. And so I don't think I have time to try this example, but it's you can just fairly easily just run, qsub simple with copper and check the results.